I'm Lauren Eatwell. I'm head of Wind Wings at Bar Technologies in the UK, and we're based in Portsmouth. This is our office building down on the water in the south of England. Our background as a company is spawned from the America's Cup. So the British America's Cup racing team, which is a sailboat design racing team based in the UK, we spawned off a consultancy or a technology company from that team and from the technologies developed by that team back in 2016 rather. And so it was from the America's Cup 35 edition. You can see the picture on the top left here is of the foiling catamarans. And that platform gave us a basis of simulation technology at the forefront of the industry, looking at hydrodynamics, aerodynamics, modeling of interaction of systems and propulsion for vessels. And we've taken that technology to apply it to green uses in the commercial industry of marine. And that's gone across several different sectors of the industry. So we work a little bit in the marine and in the leisure industry. Our first project was here, the Princess R35. That had an active foil system underneath that uses lift from the foils to reduce the drag on the back of the vessel and give great fuel savings and economy, and also a lot of roll control. That developed also into the workboat market for CTVs, so crew transfer vessels in the wind industry. And you can see our Bartech 30, which was a real combination of all of our kind of in-house simulation techniques and machine learning and design capabilities to come up with this patented Proa design hull that has active foil technology as well. So it gives really good roll stability and reduced motion sickness for the workers traveling out to the wind turbines, as well as great fuel savings and carbon reductions. The topic I'm going to talk about most today, and one very close to my own heart, is the wind wings, the Bartech wind wings, which you can see in the bottom two photos on the left. I'll go into that more in a minute and just touch on our slightly Gucci project, which is the foiler, a foiling launch that we did in combination with Spirit Yachts. And that is a fully foiling, fully electric vessel that has a range of 100 nautical miles at a cruising speed of 22 knots. So again, using our understanding of simulation technologies and developments in the industry to kind of produce cutting edge technologies. These are our wind wings, and it's been a really big year for us to go from the past few years of development of simulation and understanding of the theoretical value in having the wind technology and wind propulsion to having real wings on the water sailing around the oceans this year. It's really important to understand the background of how we got to the technology that we have. So I'm going to talk a little bit about that. We use our VPP to understand the full performance profile of what a wind propulsion technology would look like. So we're really interested in the range of angle of attacks that we want to see lift in. We want to understand the operational limits and get really accurate vessel simulations so that we can model the interactions of having several wings mounted on board, as well as the interaction between the wing and the vessel, and to balance all of our force models within the operational limits of that vessel so that we can understand the performance profile across a really wide range of environmental conditions. And to do this, along with our VPP and understanding of the hydrodynamics and aerodynamics, we use ShipSeat, which is essentially a routing tool. And we use this in earnest to back calculate what the performance profile of your ideal wind technology would look like. So instead of coming with ideas of engineered solutions, we use this routing software and performance tool to work out what the performance profile would look like of your ideal wind technology across global routes. So not just looking at ideal routes, looking at the full spectrum of worldwide trade, and then using modular design analysis to combine the effects of engine limits and propeller efficiencies along with the wing profile and performance across a range of weather conditions. So we use historical weather data and hundreds of start dates over the years to get an idea of the holistic performance of what a technology would provide in real terms, so not just in ideal conditions. And we really value our history in simulation, and it's been really important to us as well, though. It's not just our word for it. We've been validated and scrutinized by the Wolfson Unit and Lloyd's Register, who've looked at how we go about modeling, how we go about balancing all of the interactions, and to ensure that and give support to the way that we calculate it is going to be realistically how we're going to see the performance on the water. So we use this performance profile, and instead of looking for the pinnacle of design performance with a really sharp peak in the window of what we can achieve, we look for more rounded performance so that we have a wider range of environmental conditions that we're still getting almost as good as the very, very peak performance at, but over a wide range of conditions. And that we used all of that knowledge and data that came out of this analysis to lead us to what we believe is the optimum kind of wind propulsion technology. So this was the result. The result was 3 elements. You want a 3-element aerodynamic shape that allows you to fully adjust the camber and the angle of attack. And that gives us the widest range of performance across different environmental conditions. It means you don't have to constantly trim the wing so that you're getting your Ben Ainslie level America's Cup trimming of your propulsive device, and rather that you can afford to have slightly varying angles of attack of wind, and that you can adjust for leeway. You can depower your wings slightly and still get really good forward thrust. And if we look at the 3-element design, it's a lot like an airplane wing, but upright. So when an airplane wing is in flight, it's in its minimum drag, minimum lift configuration. And that's a lot more like how we would consider a traditional sail on a sailboat or a racing yacht. But actually, when we looked at the performance profile that we want, we were willing to take a hit, so to take slightly more drag in order to get the absolute maximum lift that we could. So we end up with this adjustable camber shape that allows us to get a really high amount of camber in the wing so that we can get the maximum performance and thrust out of it, and yet control that and tailor it depending on the conditions that we're seeing. You can see from the graph, we did a study, of course, and to look into the optimum number of elements to get us the ideal performance profile. And with 3 elements, we are getting 250% the lift that we would with 1 element with the same camber shape. So you're getting really big gains. The flow gets to reattach through as it accelerates through the gaps, and we get the controllability for the range of performance across the environmental conditions, across the routes, across the prevailing weather conditions. And as I said, you don't need an America's Cup sailor to achieve those. What was really important is that this is usable technology for the ships and the crews that are out there. So we have the software is delivered in 3 main sections. We have the wing control system, which sends the commands to the wing and controls the movements and the actuation, depending on which commands it's been given. The commands are given by ship seat on board, which is our module of ship seat, which sits on board the vessel and has predetermined matrix of set positions for the elements and the wing to rotate to as a whole, so that when it sees the apparent wind direction and the apparent wind speed, it's also been pre-programmed and modeled with the vessel limitations, such as engine RPM and leeway and rudder limits, so that we're never putting too much sideways force or too much power into the wings. And then it looks at the apparent wind speed and direction and sends the command to the wing control system, so the wing is set in the optimum position for the current conditions. And that works really well in conjunction with the ship seat routing application. The ship seat routing is, as mentioned by our previous speaker, the routing is essential to get the maximum fuel saving out of your wings. So we look at the weather forecast and we predict over hundreds of points of the prediction of the route that we should take. And it also considers the utilization of the engine and the efficiencies that are lost in the vessel operating at different speeds. So you can set the criteria for the routing based on your desired arrival date, your minimum fuel consumption, or constant velocity, and it'll tell you which route to take to best achieve those goals. These are the projects that we have on the water this year. So it's been a great year this year. We've had two really exciting launches. The first was the Pyxis Ocean, which is a Kamsarmax, and it has two wings fitted to it and launched in August this year, actually July this year. And then it was quickly followed by the Berger Olympus, which is a Newcastle Max chartered by Vale and with 4 wings fitted to it. One of the benefits of the wing configurations that we have is the more wings that you add, the more fuel savings you see. We don't see great interaction effects. It's very, very minimal degradation. So adding more wings gives you more performance. So the bigger the vessel, the more wings you can add, the more fuel you're going to save, and the more carbon you're going to reduce from the atmosphere. On to a little bit of numbers. So when we talk about fuel savings, we don't talk in percentages because that entirely depends on the baseline that you're using. You can use those numbers and interpret those numbers in many different ways, but dependent on the vessel, the cost of fuel, the charter rates, utilization, you're going to get different percentage savings. But what we can say for sure across the board is that per wind wing, you're saving 1.5 tons of fuel per day. So if you've got 2 wings on your ships, that's going to average out at 3 tons per day of savings. And that's for each 1.5 ton of fuel saved, that's 4.65 tons of carbon dioxide reduced from the emissions. It's important that when we talk about that number as well, that we understand how much we have degraded that number for the utilization. So that average of savings per wind wing per day is looking at worldwide routing. It's an average across the global routes of the vessel, of any vessel, an average across all the vessels that we've analyzed, across all of the routes that we've analyzed, including headwinds, including winds above 40 knots, which is the operational limit for our wind wings to produce thrust. They produce thrust up to 40 knots, but above that, they go into a feathered position where they're in a minimal lift, minimal drag configuration. So they're not saving you fuel at that time. And we've taken all of that out of that average saving. So it's a real number. If you look at the savings that you're going to get in, say, 25 knots at a 90-degree apparent wind angle, you're talking 5.5 tons per day per wing. We have vessels on the water now. We have live data coming off those vessels. We're not going public with the data yet. But what I can say is we are seeing very strong correlation between our theoretical numbers and what we're seeing on the water. This is a video to give a bit of an overview on the operation of the wings and how you would see them. So that's to give a bit of an overview on the operation of the wings, how you'd expect to see them moving. You can see it's important that they fold down to allow for port operations. And that has been a critical concern, along with how they're constructed, how they fit in with the vessel, with the technologies. We gave a strong focus on reliability, low maintenance, and robustness. So on the bottom right-hand corner, you can see the construction of the wind wing as a general overview. We've got a main spar made out of structural steel, which acts as a cantilever, and steel booms and quadrants, which are used to operate and control the position of the leading and trailing elements. There's a tilt table at the bottom with a large slew gear, so we've got 360-degree movement of the wing. And the tilt table with these large hydraulic rams enables it to be tilted flat to the deck for port operations or in heavy weather, although they can stay upright in heavy weather. Some prefer, and it can be advisable to fold them down in the most severe of storms. And then these composite fairings, which create the central element with the nose and tail piece that attach directly to the main steel spar, and the fully composite construction, leading element and trailing elements. The focus was on using materials and technology and products which exist in the marine environment and applying them to this new technology. So we don't want to be putting anything flimsy or unreliable or too high-tech or too complicated. It's robust, it's simplistic, and it's with known technology and construction techniques. You can see here, this is the metalwork in build in the factory only about 9 months ago, probably, most of these photos were taken. So it's been a really big couple of months for us, taking it all the way from manufacture. Large marine grade steel construction, marine grade paint, all very familiar technologies. And while the composite isn't used so widely in the shipping industry, we transferred a lot of the knowledge and techniques from the wind turbine industry. So here we have large clam molds for the leading and trailing elements. There's e-glass construction, pre-laminated planks that can be bonded in with secondary structure inside. So the construction is e-glass fiber infused with resin and using all of the standard wind turbine industry materials to help the supply chain, and also good known historical data of operating in a marine environment. I'd like to just give an overview of the different configurations. As I said, usability is key. So we have all this technological knowledge of how to produce the best forefront of thrust producing, maximum performance, but we really have had to consider the use as well. So the wing can be folded into different configurations to facilitate the different aspects and times of a ship's life. So these are all real photos, not renderings. They've been taken in the last few months. So we have this at sea going configuration, which allows for good visibility and easy access for tugging. This custom configuration is vessel specific. So on this particular vessel, in order to have zero beam overhang for canal crossings, we have this custom configuration. And then we have the transitioning between upright and folded, which is a very strong, slow, predictable movement. Active feathered, this is the minimum lift, minimum drag. So if you have a headwind or if you have wind speeds that are greater than the design wind speeds for the system, then it goes into this minimum lift, minimum drag, and actively is driven into the wind direction to ensure that it's minimum drag on the vessel. And then, of course, the max lift sailing configuration. And then for the port operations. So we're lucky enough, I was lucky enough to go out to Poland last week and see the Pyxis Ocean for the discharging of its first load of cargo. And it was excellent to see the full cycle then of all of the configurations and design conditions that the wing has been designed for being fulfilled. So in cargo loading, it has this low profile hatch clearance position. And then for the cargo discharge, we were able to use this maximum clearance position with slightly greater height. So thinking around holistically the aspects of the wing's usage, not just the fuel savings. So that is a flyby visit to particularly the past year, but the years in development as well of the Bartek wind wings. And the key takeaways of what we've found are that this patented 3-element technology gives us the maximum performance in terms of angle of attack. So we can have wind directions of up to 10 degrees off the bow, apparent wind direction, and we're still getting forward thrust production. And we've got this forgiving shape and the ability to reattach the flow so that while the wind's fluctuating fluctuating, we're getting still really good performance, a really forgiving shape. Very minimal interaction effects. So the more wings, the more fuel you're saving. Practical, reliable construction that we've seen now throughout the different phases of its operational life, folding and stowing to allow for port operations. So a technology that's out there proving itself, and the 1.5 tons of fuel saved per day is pretty close to what we're seeing. In reality, we're matching our simulations with our expectations. And as I said, on any given day, we're seeing far in excess of that. Well, we've seen easily 6 tons per wing per day in the right conditions already. Thank you very much.
Okay, well, thank you very much, Lauren. We have a minute or two if there are any questions. Sergio, I'll turn this around and see if we can.
Thank you for really great presentation, very encouraging, makes me very optimistic. Can I ask you, do you know what kind of, can you tell us what kind of lift coefficients you're getting out?
I'm sorry, I didn't catch that question.
The question was, could you tell us what sort of lift coefficients you're expecting?
Yes, I think we're seeing about 2.5 lift coefficient, but the real advantage of this technology is that we're seeing that in a really wide range of wind directions.
How about drag coefficient?
The next question was, how about drag coefficients?
I don't have that on the top of my head, I'm afraid.
Yes,
what's the cost effectiveness of that addition?
What is the cost effectiveness of the addition?
What fraction of construction cost of the ship is sales?
So what fraction of the vessel cost are we expecting?
Well, I can't give you an answer to that straight off either. It depends on the vessel cost, what fraction of the vessel cost it is. But we're seeing really good payback periods. And again, that's something that it's hard to talk about because it depends on your baseline of your fuel cost. But easily seeing kind of 4 to 5 years payback period, even better if we're talking about increasing fuel costs, carbon taxes in the future. So the return on investment's there. And then, of course, the fuel is free from there on out.
Okay, we're going to move on to our next one. Thank you very much.
You're very welcome. Thank you.